Hello and welcome to today's Tech Talk. My name is James Skelton. I'm an evangelist at Paperspace, and today we're going to be talking about AvatarCLIP, which is a very nifty new algorithm for generating and animating 3D models. So these are typically human figures. If you're not familiar with Paperspace Gradient, Gradient is a platform for building and scaling machine learning applications. Within Gradient, you can explore a new library or data set in a notebook, which is very similar to a Jupyter notebook, automate pre-processing, training, or testing within a workflow, and bring your application to life by deploying it. I would love for all of you to join our community of over 500,000 users on Gradient today. And without further ado, let's jump into AvatarCLIP. One second. So here's an overview of what we're going to be covering today. We're going to start off with an introduction on AvatarCLIP, just talking about what it is in a very shallow look, and talking about when it came out and who the authors are. Next, we'll start with some introductory material about 3D human figure modeling. This is material I think is necessary to understand what's really going on with AvatarCLIP. Next, we'll talk about motion synthesis and some background on previous work in motion synthesis and how they achieved motion and animated figures. And then some background on CLIP and getting zero-shot text generation using CLIP, talking about its utility and ubiquity. And then we will finally jump actually into talking about AvatarCLIP, talking about what it does in each of the different stages of its pipeline. And these are specifically static avatar generation, avatar texturing and sculpting, and then motion synthesis. We'll then close the slides with an overview of the actual architecture pipeline, so looking at how it achieves these things, and then jump into a code demo in a Gradient notebook. Over on the right here, I've got just this image from the original paper talking about what AvatarCLIP does, and I just want to start with a look at this. Here we've got 4 different kind of sequences or images with their own prompts. So the original one is a tall and fat Iron Man that is running. So we've got this it's supposed to be a tall figure that is chubbier and certainly chunkier looking than the Iron Man I'm sure all of you are familiar with from Marvel. And here we have a series of different poses it will take. So AvatarCLIP creates this static model, skins it, textures, sculpts it, and then puts it through a series of poses to give it a animation sequence. All right. Go to the next slide. So AvatarCLIP was introduced very, very recently. In fact, the paper is set to technically release in, I believe, July. And the paper was originally titled AvatarCLIP, Zero-Shot Text Generation and Animation of 3D Avatars. And what it functionally does is use text prompts to zero-shot generate animated, sculpted, and textured 3D models with just Python code and access to skinned multi-person linear models. So those are the 2 prerequisites for running this that you absolutely need. You need to be able to run this with Python and to use SMPL. On the right, we've got a more active demonstration of what AvatarCLIP is doing. So we talked in the last slide about how it will put them through a series of different poses here. Here they are actually acting out those poses. So in the first one, we have a tall and skinny female soldier that is arguing. We can clearly see that they're wearing something like military fatigues and a feminine body shape, and they're making hand motions to give us the idea that they are arguing. The next one is a skinny ninja that is raising both arms. We can see that this figure is also thin, and they are raising up their arms above them. And finally, an overweight sumo wrestler that is sitting. Here we can see kind of some of the limitations of AvatarCLIP, but we can still see it doing a much different sequence of animation But because there is no chair or bench or whatever to sit on, it can look a little funny in comparison to the others. So already we're seeing the utility and limitations of AvatarCLIP for creating these 3D animated figures. Excuse me. But they are unable to interact with some sort of existing space or objects using the existing code. All right. Next, let's talk about some of the needed background information. In these slides, we're talking about 3D human figure modeling, and we're going to start off with SMPL. SMPL stands for Skinned Multi-Person Linear Models, and SMPL is a realistic 3D model of the human body that is a skinned vertex-based model that accurately represents a wide variety of body shapes and human poses. I want to draw attention to what it means to be vertex-based. This essentially means that throughout the model are different pivot points. You can think of these as being kind of mimics to actual human joints. These are places that can be moved to adjust the shape and pose of the figure, but they're not truly human joints because you can do, well, like if you were to put somebody's elbow vertex all the way back there, it could have a very inhuman shape. For its strong interpretability and compatibility with the modern graphics pipeline, the authors of AvatarCLIP chose the parametric SMPL as the template for their avatar, but it's worth noting that SMPL really only gives them the ability to model that human body shape. So that is without clothes, without accessories, without the different things that would, make a skinny ninja look different from a female soldier. On the left here is a figure I want to draw attention to as well. Here is a bunch of different poses and shapes the SMPL can take, and we can see how it is then mapped to the ground truth 3D meshes, in this case used with Unity, to actually animate the figures. So SMPL is used in a lot of different places, including this AvatarCLIP pipeline. The next human figure modeling concept I want to introduce is NUS, or NEUS. I'm actually not totally sure how it's pronounced. They introduced it to model clothing and accessories because non-parametric models actually perform a lot better dealing with these types of additional add-ons, so to speak, to a figure. NUS is a non-parametric neural surface reconstruction method for reconstructing objects and scenes with high fidelity. So it's not just people. They can basically generate high quality geometry and color reconstruction from 2D image inputs, and then output that onto a 3D figure. NUS represents a surface as the zero level set of a signed distance function, which we'll go into more detail later, and uses its own volume rendering method to train its neural SDF representation. So over here on the left, let's move this up here, sorry. I have a figure for us to look at for NUS, this bottom one. Here we have a reference image and then different surface level representations of that reference image from kind of previous iterations of non-parametric models a la NUS. And then the final one is NUS. And as we can see, getting a lot more detail here. It feels like it's actually capturing this depth completely, whereas this NERF, which was released just a year ago, kind of fails to get that full understanding, and IDR almost seems like it has like a water layer or something floating on top. So they used NUS because it was the most effective that they'd found, and they actually made some small modifications to it that we'll talk about. But for now, all you need to understand is that in the AvatarCLIP pipeline, SMPL, NUS, and NUS work in tandem to sculpt and texture the 3D figure that is the, the 3D figure. Next slide. Next, I want to talk about motion synthesis. One thing that I just realized now I haven't mentioned yet is that motion synthesis actually is not going to be a part of this presentation in the code demo because the code has not been released publicly. We will likely do a part 2 of this talk when that is available, but I figured it was worth still including all of this because it's a part of the original paper, and the full pipeline is more interesting than just a portion of it. That being said, I still think it's worth talking about motion synthesis and what's going on here because it's very interesting, and a lot of the work that's being done is cutting edge. So 2 recent works that cover similar challenges of animating a 3D figure are Action to Motion and Actor. In these papers, their models condition the motion generation on pre-selected action classes. Actor specifically works by sampling from the latent space and querying a certain duration through a series of positional encodings to synthesize variable length motion sequences conditioned on a categorical action. So if we look on the right here, we have a figure from the Actor paper, and here we can see a bunch of different inputs: left stretching, pickup, side kick, throw, rope skipping. As they are inputted to this action condition transformer variational autoencoder, it generates a sequence of different poses that represent this categorical action. So left stretching shows that full range of stretch. This is my right, but whatever. Pickup shows bending down to pick something up. Side kick shows a kick out to the side. A throw has a throwing motion with the arm, and rope skipping imitates jumping rope. While this is pretty robust, like as you can see, these are actually pretty good approximations of these actions. These methods require, frankly, absurdly large amounts of data with annotations of action classes or language descriptions, and that limits their applications in a lot of ways. AvatarCLIP differs from this because it does not require any paired data. I got a comment. It reminds me of the work at the Max Planck Institute for Intelligent Systems. Yeah, SMPL is, I believe, from Max Planck. Yeah, 40% sure. I can't confirm that. I think in order to get it, you need to actually go on there and sign up. And I'll talk about that later. If you want to follow along, you actually have to go get the license for SMPL. So it makes sense that you're seeing similarity there. Oh, perfect. You're already set up. Honestly, it may be worth it just to call attention to that. You can go to the SMPL website, make an account, and download it. That's one thing you can do while I'm talking. Everybody, if you want to actively participate in the code demo later, but it won't make it one-to-one because the code takes quite a long time to run. So I wouldn't stress about that. It's just something we could do. Anyway. Let's move on to the next slide, talking about CLIP. So, as I just said, CLIP actually takes out a lot of the hassle because we need so much less data to actually make AvatarCLIP do the same sort of work that Actor or the other one whose name I'm forgetting does. If you're not familiar with CLIP, CLIP stands for Contrastive Language Image Pre-training. And it's a vision language pre-trained model trained with large-scale image text pairs that allows for zero-shot text-driven image generation. It can be instructed in a natural language to predict the most relevant text snippet given an image without directly optimizing for the task. Similarly to the zero-shot capabilities you might see in some of the more popular NLP algorithms like GPT-2 and 3, or Neo-X, whatever they're on now. It's been proven over and over and over to be excellent at supervising the generation of 2D images based on text prompts, but this does not directly translate to working with 3D images, and some work had to be done to actually make it correspond with AvatarCLIP that I'll talk about later. For now, what you need to understand is that CLIP can actually supervise the generation process in such a way that it doesn't necessitate the large amount of data in our in the other aspects of our image generation. At the bottom here, I've got an example of one paradigm that uses clip. This is from StyleGAN to face, which is used to generate just faces based on captions inputted. As you can see from the generated images above, we can use clip subversion to directly input the desired captions to generate 2D images for numerous different applications. This can be done for everything from full bodies to, I don't know, cars to scenes. It's a very, very robust supervisor. What's the name of the website for the download? I had a question. I figure I should actually, since I said that, let's really quick get the SMPL page. So here is the link. Again, it's going to take a minute to actually get it uploaded and working with, but what you do is you go to sign in, and if you're not already registered, register to make an account. Then once you've registered and signed in, you can go to downloads with this link and download a zip file containing SMPL. It's .1.1.1, I believe. And then when we get to the code demo later, and I'll talk about this again, I promise. What you would do is you go to upload files, which will be here in the top left, and then you can upload whatever SMPL you need to upload. Cool. Does that answer your question, MM? Just want to make sure. Beautiful. Okay, so now we have gotten through our background slides, and we've got a pretty decent understanding of what's going on to make this happen. Let's look now at how it is all put together. So, AvatarCLIP, what does it actually do? Well, it works in 3 parts. First, coarse shape generation. It needs to generate a starting figure to work with in the following stages. To do this, it uses clip to take in a text prompt to check a codebook for a suitable model to output. And I'll go into a lot more detail about what this means in the next slide. Avatar sculpting and texturing is the next stage. It then sculpts and textures the coarse figure that we've generated, and it does this via a series of color and SDF networks that operate on the original avatar. And it uses clip to guide the construction of the final figure. Finally, we have the applying animation sequence to the generated avatar. Again, this part will not be included in the final code demo, but it seemed necessary to include everything. It applies to a model a sequence of poses to generate an animation, and it does this first by generating a series of candidate poses based on a clip-guided text input, and then using the marching cube algorithm to apply these poses to the textured avatar. So, just to round it together in a much shorter way, we generate a coarse avatar, so a rough shape. We then sculpt and texture this avatar to look like whatever our desired figure looks like, and then we apply the animation sequence to get our final output of an animated avatar. And really quick, I'm just going to go back to the start so you can get an idea of what that is. So we start with this, this isn't the coarse shape. We would start with a coarse shape kind of like these SMPL. It'll actually be grayed out, kind of the same color scheme we see here. Then over the course of the second stage, we get towards this colored sculpted version. And then in the third stage, the sequence of poses is generated and then applied to get us to our final animated figure. It's really cool. For any of you that have ever worked in animation, this has the potential to save thousands of hours in animation, so the utility is really immense. Okay, let's talk about coarse shape generation. Excuse me. I actually have another overview slide. Pardon me. Let's put it all together with a visualization. So here we have an overview of the entire pipeline for AvatarCLIP that I'm going to walk us through before we jump into the specifics. As you can see, we start off with our coarse coarse mesh MT here that is based on our input T shape. So if it's a tall and fat man, we get it'll look taller compared to other figures, a taller figure that is chunkier, and we can see they've got the adipose tissue spread throughout. This is done by choosing from a code book of shapes and finding the highest scoring one that corresponds to the initial input T shape. From there, two different things happen, though not really simultaneously, as is implied by the image in front of us. The T appearance value, or T app, is used to sculpt the shape and then add texture to our mesh using the noose model that we talked about earlier. It's able to look at a multi-direction view of the model, as shown here, to further sculpt and texture the existing figure to approximate TAP as closely as possible. Clip supervision throughout ensures that the originally featureless model over time moves closer and closer to the text description as we iterate through the training loop. In this case, it would be to look like Iron Man. Once we have our final model that is sculpted and textured as desired, we add the marching cube algorithm to get our animatable 3D avatar. Like I said, not simultaneously, but also happening to this process is adding motion. To do this, we have a T motion input. In this case, it would be running with clip to generate a sequence of candidate poses from a code book of potential poses. Input with clip to generate a sequence of candidate poses from a potential code book of potential poses that matches the motion described in the text T motion. Again, in this case, running. We then create a reference-based animation of a coarse avatar with the motion prior sequence. So a coarse avatar that corresponds to our coarse shape is then animated, and then we apply that to our final sculpted 3D avatar to get a 3D moving, sculpted, textured shape. Cool. Let's talk about each of these stages in some more detail now. Okay. So to generate the starting mesh, the authors used what's called a shape variational autoencoder to build a code book of all the potential combinations for SMPL by clustering the common body shapes. So they clustered the common body shapes and basically built this code book around those centroids. Then clip is used to extract features of the renderings of body shapes in the code book to get the best matching body shape to the text. They define a natural body state. Here it's TN, and we also have T shape. And they basically compare them and then score each entry in the codebook by calculating the score of each codebook entry with the neutral body state in the text value, and then they output the highest score as the coarse shape. So we have this very different looking one and what it thinks should be right, and it is moving us away from the very different and towards what it should be right. Once we have that, we have our final outputted coarse shape, in this case, a tall and fat man that we will then use to texture and sculpt in the next step. Cool. So for avatar texturing and sculpting, first the mesh MT is used to optimize a randomly initialized noose network in. This creates an implicit equivalent representation of MT. The noose network is comprised of two multi-layer perceptron subnetworks. These are the SDF, which we talked about earlier, that takes some point P as input and outputs the sign distance to its nearest surface, and the color network CFP, which takes some points P as input and outputs the color at that point. This noose network serves as the initialization for the fine detailing and sculpting of the method, but on its own, the authors found this was insufficient for the task. While the model could add textures to a coarse figure, it really couldn't make any substantial changes to the geometry of the figure in the just SDF and color network mode. To add the capability for sculpting changes to the volume of the mesh and colorizing these parts, the authors appended an additional color network for the initialized implicit 3D avatar so that they can do texture generation. And we can see here this additional color network below. And each of the color networks works with the SDF network for different tasks simultaneously. The original CFP, so this one, the top color network, and SDF network are used to reconstruct the mesh MT using guidance from a clip text encoder to match the TAP prompt, and the CCP, or the additional color network, and the SDF then perform the finer level detailing guided by the clip encoded image. Using clip guided loss, together the system will then generate a fully detailed figure that approximates the input prompt in terms of shape and detail, but without a pose. So it has this starting, not T pose, Y pose or something, and it colors and textures it to best approximate that. One thing I want to draw attention to here that I haven't really talked about much yet is I've said texturing and sculpting a lot. And I should clarify what those mean. Texturing is adding the color and the sheen, I suppose. So that's what gives Iron Man his red and silver and gold suit here. And then the sculpting is actually adding on the accessories or little changes. So for Iron Man, this is like the chest plate thing here, which it doesn't totally get right. I'm noticing now that's a hexagon. That's amusing. And things like that. But let's say we were working with, I don't know, I'm trying to think of an example. Batman. Batman has his pointy ear things. Those would have to be sculpted on to the final figure. These are all things that you'll run into, but it's pretty good at handling it, especially for the pre-existing examples that we can work with. Okay. Finally, motion synthesis. So to achieve motion synthesis, first, the Martian Cube algorithm extracts the meshes we created for our static avatar before making it animatable. This is simple because the optimized mesh aligns with the initial template mesh for all SMPL models. So the way we have done the sculpting and texturing, it does not affect the actual vertices and shape of the SMPL model. So we can do anything we would do to SMPL that we would to our final output. Second, a pre-trained variational autoencoder called vPoser is used to build a codebook of representations for the prompts using the AMAS dataset. The AMAS dataset basically is a collection of different poses that people can go through. So this is this codebook is a representation of different poses grouped together. Third, we generate a sequence of candidate poses consistent with T-motion in a paradigm that is very similar to the way we textured our figure earlier. The score, given the texture description T-motion, each pose feature Fi from the codebook is used to calculate the similarity with the text feature F of T, which is then used to select the top K entries as the candidate poses. So we are left with a sequence of poses that are not really ordered, but are similar. Using a pre-trained motion variational autoencoder, so this is a different VAE, given the reference poses S, we construct a motion sequence that is close enough to these poses. And we use the reconstruction loss L pose to optimize the motion sequence. Reconstruction loss from the poses with just that L pose tends to cause an oversmooth output. As you can see down here, this oversmoothing effect basically makes the motions conserved, so to speak. They're less dramatic, less extended. So to give a wider output, or to give the output a wider range of motion, an additional loss term is used to penalize oversmooth motions called L delta. Finally, we use CLIP to supervise and order the sequence by measuring the loss and similarity score between the candidate pose and the original text prompt. And this outputs the sequence in the order desired to emulate the animation motion we want. So we are left with a sequence of poses that can then be applied to our 3D mesh to make it animatable. That is our textured and sculpted 3D mesh. Putting it all together, we get our tall and fat Iron Man that is running. As you can see, he kind of takes off there before he goes into a full sprint. In full, it takes 3 text inputs. That is our T-shape, T-app, and T-motion to generate a fully animated sequence on a textured and sculpted 3D avatar. It does this in 3 stages. The static avatar is generated first with SMPL and the shape VAE. Then an implicit noose representation is then used to functionally apply fine detailing, texturing, and sculpting. And finally, the marching cube algorithm is used to apply the animation sequence we determined with the variational autoencoder in the previous slide to the model. Altogether, we get this beautiful little GIF here showing the full sequence. And you can see how the 3 text prompts could be put together into a single sentence. I'm so sorry. Excuse me. We can see how the 3 inputs could be put together in a single sentence input, a tall, fat Iron Man that is running. So we have our T-shape, our T-app, and our T-motion. All right. So for the next step, we're going to do a code demo. To follow along, let me pull up those links again, one moment. To follow along with me, you can either click on the link I just sent in the chat and then go to the second to last slide to get the link to the run on gradient code demo. You won't be able to run these cells, but you will be able to see the work and download the files or whatever if needed. Sorry. But otherwise, I recommend that everybody follow along with me so we can create a new gradient notebook so that you can do this on your own time after this session. So to do that, really quick, once again, I'll just point out, this is where you get your SMPL. But to do that, let's go to consult.paperspace.com. Okay. And then what you need to do is either register if you haven't or sign in, and then go into any project of your choice. Once you're in there, go ahead and click this create button on the top right, and this will take you to our notebook creation page. Within this notebook creation page, you're going to want to select a PyTorch runtime. This will have all the PyTorch suite pre-installed onto your instance. And then for your, it looks like we don't have any free GPUs available. For your machine, try and select a free GPU. If it's not available, you can do a paid one if you have a paid account, but otherwise just follow along with me for now. Usually the free GPUs are more available at less busy times of day. People are working at lunch, or it's the evening in Europe right now, so possibly hobbyists are on there right now. That could explain why the free GPUs are all taken up despite our rather impressive volume. And then finally, the last thing you need to do is you're going to need to take this URL right here and paste it where it says workspace URL. What this will do is it'll take our GitHub repo that it's just a fork of the original AvatarCLIP repo, but it'll take ours, which has a gradient, an IPython notebook already in it, so that you can run all the code that we're going to be talking about today on your notebook. If you are unable to make a notebook at this time because of the free GPU limit, I'm sorry about that. Try again later today. And just recall that the instructions for setting this up are all right here on slide 15. If you were able to do it, all you need to do is click Start Notebook, and then it'll push you into a gradient notebook that looks a la this. Can I get B's in the chat that we are all ready to move forward. Just don't want to rush ahead if anybody is trying to make this work and is waiting. Gracias, Guillermo and Prajwal. All right, let's jump into it then. At the top here, I've got just some information about this. Yes, sorry, you should create the Paperspace account if you don't have one. Let me. It's not letting me make a new. I can't make a new page, so I can't sign out right now. Otherwise, I'd show it. But at the end of this session, I'll walk through how to make an account if you want some help with that. But yes, you need to make an account to follow along, or you can click on that link at the end there. That will open up. Oh, here we go. That will do something like this. So it creates a fork of the notebook, and you can view an offline version. It still has all the same files. So if you wanted to access what it would look like in a gradient notebook, even though it can't run, you can use this offline version. Cool. Sorry about that, y'all. So at the top of the page, as I was saying, there's just some information about what this is. This is an adaptation from a notebook created by the original author team, Hong et al., I should say. It has a relatively quick example for shaping and sculpting a static avatar, but it does not include the motion portion of the code. I will add that in as soon as it's here, but it's currently not in the repo for the original. I definitely recommend visiting the original repos and project pages for this. You can get access to the original paper from there too. Oh, this isn't the original paper, whoops. But still a very, very interesting paper. I definitely recommend reading through if you want a more in-depth look at what we talked about in the slides. All right, let's get started with setup. So the first thing you need to do when you are in this notebook is to run this cell. What it'll do is it will clone the AvatarCLIP and neural renderer.get. Well, oh, you don't need to actually run this one. Excuse me, that's a typo. You just need to clone the neural renderer repo and install the requirements for AvatarCLIP running this cell. Then this cell makes a small change to one file, the perspective.py within neural renderer that makes it actually run. Basically, it has problems if you don't make this change. This is just an author inclusion in their original notebook, so I didn't figure it was worth changing. Next, some additional housekeeping and imports set up for the environment. For whatever reason, the requirements installs an old version of NumPy, so rather than hashing that out, I've just got an updated NumPy install here. We're also installing scikit image. And we're installing the same repo we cloned earlier, neural renderer, as a package. So you run that cell, and then this next one will have two different instructions depending on who you are. If you are running this in a paid notebook, then you can run this in a terminal by going over here to the left and clicking this to add a terminal, and then pasting the values within. You should not need to do this. Well, okay, excuse me. Yes, you will need to do this no matter what. If you are on a free account, however, this may prove to be a problem because free accounts don't currently have terminals. The workaround currently that I'm trying is to install OpenCV Python headless. This doesn't require libgl to work. So give that a shot. I'm sorry, I haven't tested it yet, but that may be a solution. You also need ffmpeg. Finally, to finish the setup of the environment, we're going to run this setup.py install from neural renderer, and then change our working directory to appearanceGen, which is a part of AvatarCLIP, AvatarGen, appearanceGen. Next, we have the SMPL model set up. So, as I said before, you need to register and download the SMPL models yourself. This is because they do not allow distribution of SMPL except for by themselves. So you need to do it on your own and directly upload it. Shouldn't take too long. It's only about a gig. To do this, you go to smpl.is. I'm not going to read the full URL and sign up. And then once you do that, you go to the download.php page and download SMPL_Python v 1.1.1.zip. Third, upload it to this notebook. Again, you can do that by clicking here, upload files, and then going to SMPL, do the zip version. If you're on that's a good point. If you're on a free notebook, don't do the zip version because then you'd have to unzip it using Line Magic, which you can do, but it'll be more complicated. That would be something like, unzip SMPL Python v. Is there an underscore? Yes. v 1.1.1.1. And that would work. Sorry, I'm sorry I haven't responded to this question, you asked, will I be able to send out a copy of this recording? Yes, you will all get a copy of this recording, and I will post it on YouTube. So be sure to check out the Paperspace YouTube channel for previous tech talks as well as this recording. So really quick, going to finish up this SMPL section. Once you have uploaded the notebook, you can unzip it by running that code. Looks like it actually needs to be more like this. The reason we have to do it this way is because earlier we changed our directory to the neural, I believe it was the neural renderer. No, appearance gen. So we're 3 directories deep, and that's why it has this awful syntax. Or you can do it within within your terminal if you're not on a free notebook. Once you have SMPL set up, that is everything. So we can actually get started with running the code. This cell is our imports. It's using a ton of different libraries, but notably these are the ones that we installed with AvatarCLIP. Next, we have our, I guess you could call it parameter cell. Here we're going to input our appearance description. That is the T app. So that's the only one that's really being acted on here. We are using a neutral body shape just to simplify this process as much as possible, especially because the more interesting part actually is the detailing and sculpting of the figure. So for my example, which I've actually had running since before we started, because it can take 2.5 hours to run 10,000 iterations of this, is on Batman. And if you want to see a full list of the potential examples you could work with, go into your repo, go to AvatarCLIP, AvatarGen, AvatarGen, Appearance Gen, and then Confs, and then Examples. And then here we'll find a ton of different examples with everything from Draco Malfoy to literally Drake, the rapper, to, oh gosh, what's the most absurd one I can find in here? I'm assuming, is Panther just the Black Panther, like the Marvel character? I don't know. You can do a quite wide variety of still human characters. I think the most alien-looking one would probably be the Gundam, which is, or Godzilla. Godzilla it is. Godzilla or Gundam. If you want to try something that is totally different, non-human looking, try the Godzilla or Gundam examples, and you can do that simply by changing here in conf path the confs examples, and then, you know, if you want it to be Godzilla, put in Godzilla. Cool. So you change your appearance description caption and the conf. And then once that is all done, we can go to the next cell, which will have our runner. This will, the runner basically does the actual, what's the word I'm looking for here? The actual sculpting and texturing. So it initializes clip and SMPL, and then the train clip module actually does the running. So it's training with clip to output the desired output. Since this has been going on for so long, I can actually refresh my Explorer here on the left. Of course, I've put in many different things in here, so that's why it took a second to refresh. It said, yeah, as you can see, giant file at this point. Close these. Okay. So it looks like currently it is still finishing up, so I can't show you my example for Batman, but I prepared some other, I guess, all Japanese themed ones here for you to look at if you're on my repo. So you can just click that link I sent earlier. Let's just grab it again. If you want to look at these right now yourself, regardless of whatever path you're taking to do this, you can just click on this link and then go down to, let's see, get into Avatar Gen, then EXP, example, and then validations extra fine. Oh, not example, sorry, examples, and then you'll get your outputs. In this case, the ones that I did. So let's use a good one. Gundam was short. I think Saitama was my longest one. But if you're not familiar, Saitama is the main character for the popular parody show One Punch Man. And he does kind of look vaguely like this. Let's pull up an image. It's kind of going with Superman colors here. So let's check if the normal has a better coloration. No, validation's fine. Yeah. Okay, so you can think of I would think of the validations extra fine kind of as your final output. It seems to think because Saitama superhero, Superman colors, I'm guessing that's why the coloration. But yeah, that in a nutshell is AvatarCLIP. That is like the full code that we're going to be really talking about today. There is one last part I'll mention. These two snippets here will generate a video of the optimization process. So I just showed you that example of what Saitama looks like after 10,000 iterations. Let's get this here. If we look at his start, it's actually pretty nothing. But he slowly gains color and shape using that SDF and color network. Well, SDF and color networks, I should say, towards our final, which is even starting to get some of the facial expressions that he has. So if you want to look at that in a more detailed manner, I actually have an example here. Let's just open that up. This one is for a fat Iron Man example I had. This is their default code to run. And if you run it for, I think it's 3,000 iterations, you will get this. So not quite up to the standard they were showing with 30,000, but still, I can tell that this is supposed to be Iron Man. And we can see how, if given more time, it will start to more closely approximate our inputted appearance, and then eventually get to these kind of more high quality shapes that we're seeing here. Here are just some more examples. I rather like this Yao Ming one. Our fork of the repo is here. This is where you can get access to the IPYNB file. Again, you can get a fork of my gradient notebook by going here. And you can download SMPL by signing up here. I think that's all the important links. But yeah, definitely be sure to play around with AvatarCLIP. If any of you are involved with animation or anything with 3D figures, I know you see the incredible utility of this. It's really amazing. We'll see if this ever gets strong enough to replace some of the more mundane work that animators have to do, just making people go side to side or to walk in the background. Imagine the thousands and thousands of hours that could save by doing that. It's actually really incredible. But yeah, thanks so much everybody for attending. If there aren't any questions, I will end this call in a minute, and y'all are all good to go. Really